Welcome everyone to this very special AI Salon event. I'm Abby and I'm a PhD student in the Stanford NLP group. I'm very excited to hear what our two speakers have to say today about a question which is of central importance to AI research today. And that question is, what innate priors should we build into the architecture of deep learning systems? This discussion is about what kind of design decisions we make in our neural architectures. When we design a network to have a certain kind of structure, or lack of it, what inductive biases are we introducing, and what innate priors are we assuming? Should we be designing our neural networks to have more structure, or less? And what kinds of innate priors should we aim to capture via these design decisions? We're fortunate to have two wonderful speakers today. We have Yann LeCun, who probably needs no introduction, but he is a deep learning pioneer and the founding father of convolutional neural networks. We also have Chris Manning, who is a world-leading NLP researcher here at Stanford, and he's published highly influential work applying deep learning to natural language processing. This event was recently described on Twitter as the AI equivalent of Superman versus Batman. Which I think raises some interesting questions. About who would be who. But I think actually we're going to find there's many things that Chris and Yann agree on. So the interesting part will be figuring out what they disagree on. Before we get started, I'm going to tell you about the format of this session. First, Yann will speak for 5 minutes, giving an overview of his thoughts on the topic. After that, Chris will do the same. And then the two of them will have a conversation for about 25 minutes. After that, we're going to have time for audience questions for about 20 to 25 minutes. There are microphones on either sides of the stage where you can queue up to ask your questions later. I'll be here to make sure that we keep to time, and I'll intervene in case we wander off topic. Lastly, I want to note that AI Salon is inspired by 18th century Enlightenment era salons, so it's a no electronics zone. All of us will be using no electronics, no slides, just paper and thoughts, and conversation face to face. So please could you also not use any phones or laptops during the session. Okay, that's it. Let's get started. Yann, you're going first.
Okay. So the first thing I should say is that this is probably something we're going to agree on, which is that prior structure is necessary. Something we may or may not agree on is that it's a necessary evil, in the sense that, of course, there's all kinds of theorems, no free lunch theorems, for example, in learning theory that tell us that without structure, you can't learn anything, essentially. Or you can't learn anything without a ridiculously large amount of training samples. And so necessarily, we need to put structure to be able to learn anything in a reasonable amount of interactions with the world. That said, the history of pattern recognition, AI more generally, but more specifically pattern recognition, speech recognition, for example, handwriting, computer vision, has been one where the amount of prior structure in our systems has been shrinking and shrinking more and more. And that has been a consequence of the fact that our data sets have been increasing in size. And so there is no absolute statement we can make about how much prior structure we need, because that depends on how much data we authorize ourselves to use. So if we put ourselves in the context of either supervised learning or reinforcement learning, where essentially the type of feedback that the machine gets is directly related to the task it's supposed to achieve, then clearly there is something called the sample complexity of a task or a particular machine. And you will need a particular number of samples for the machine to be able to learn a particular task. And the more specialized the machine is, the fewer samples you will need. On the other hand, the more likely it is that the structure you put in the machine is wrong. And in fact, what's happened over the last several decades, the reason why people in speech recognition, handwriting, etc., have been putting less and less prior structure in their systems is because any structure you put in, you make an assumption about the nature of the data, and that assumption generally tends to be wrong for a small percentage of the data. That limits the minimum error rate you can get. As we get more data, more supervised data, more labeled data, or as we get more powerful machines that, which allow them to interact, to do more trials for learning a particular task, the amount of structure we need becomes less and less prominent. Now, so that's kind of one side of the kind of a historical perspective on, the amount of structure kind of diminishing. Now, of course, things like convolutional nets is actually all about structure. So obviously, I'm not against structure, but it's a necessary evil for the reason I just mentioned, which is that every structure you put in, you make assumption that might turn out to be wrong. Now, at any particular point in history, for the kind of techniques that we have access to, we might need to put structure so as to get results in a relatively short term. And that structure may turn out to be useless 5, 10, 20 years later when machines become more powerful, more data is available, new techniques are invented, and the structure may become less useful. And so it's difficult to make an absolute statement about this. Now, so what is the situation today? Like, how much structure do we need today? And in one area where I think we might be agreeing on is where deep learning and machine learning in general have kind of are trying to push the frontier, but are limited at the moment, is the area where you can marry machine learning with reasoning. So we don't have really good techniques so far. There's a lot of people working on it, including Chris, on how you get machines to reason, not just perceive, not just arrive at a result with a finite number of steps, but kind of think about something for a while. So how to marry inference and learning. And then I think there is another question, which is possibly a way to get out of the conundrum, which is not training a machine for a particular task, but training a machine to just learn how the world works and then fine-tuning it to a particular task afterwards. And I think that's the kind of learning that humans and animals do. And that's one of the things I'm very interested in at the moment. The question of structure there is a completely different one.
Okay. Maybe I should just say a little bit about where I originally came from. So my background is starting off largely as a linguist. And so as a linguist in the field of linguistics, Noam Chomsky is this sort of singular figure which has sort of dominated an academic field in a way that few people have. I mean, maybe for statisticians, he has a status similar to R.A. Fisher had in the sort of 20s, 30s, and 40s of completely dominating an academic field. But, he certainly far more dominates linguistics than something like, Michael Jordan dominated machine learning in the 2000s. And as most of you probably know, that Chomsky has always had extreme views in believing in innate structure. And in particular, around the time I was coming into the field, he developed this even more extreme version of the principles and parameters theory, which, if taken literally, essentially said that variation between two different languages was limited to setting some binary parameters as to whether you put verbs at the end of the clause or in the middle or at the beginning, and then learning labels for concepts, which he also argued were innate. So as a sort of a 20-year-old as an undergrad, I was on Yann's side. I thought this was completely wrong and could not possibly be the way the world worked. And even with the very nascent forms of machine learning that were being developed in the 1980s, it sort of seemed like, well, surely we could do some stuff here and start to learn some things. But on the other hand, I think you can go far too far in the direction of empiricism and thinking, well, we can just learn all our things. So I think I would like to differ a little from Yann in regarding the sort of the structural priors or that you're building into a model, not as a necessary evil, I think as actually a necessary good. So although in some sense we've now built learning machines that are very successful, in another sense, I think we haven't built learning machines that are very successful at all. So if I stick to my linguistic roots, I still believe that child language acquisition is completely miraculous, and you really don't appreciate how miraculous it is until you see it up close for yourself, that you kind of have this kid that's stuck for months in a 1 and 2 word stage where they can sort of say juice, want mummy, and then it sort of seems like suddenly something clicks and they think, oh my God, this is a generative system of recursive language and I can produce big sentences. And then suddenly they're saying, 2 weeks later they say, baby Casey put the stuffy in the box under the sofa or something like that. That there's sort of something amazing that happens there. And I think the answer to that is having rich innate structure in the learning device. And I think that's the only way that we're going to get the kind of rapid learning that human beings have done. And so I think this current era, we can get more specifically into machine learning later, but I think this current era where everyone tells this mantra of, fast GPUs, massive data, and these great deep learning algorithms has hugely sort of perverted the field and sent it off track, because it is the case that if you have huge computation and massive amounts of data, you can do a lot of stuff with a very simple learning device. But those learners are extremely bad learners. Human beings are extremely good learners, and what we'd like to do is build artificial intelligence devices that are also extremely good learners. And I think the way to achieve those learners is to put much more innate structure, much more ability to learn into our machine learning architectures. And then the question is how to do that in a way that is good. So I certainly believe you don't want to do it the way that Chomsky has argued. Yann was making the points about how you're putting in these priors can, limit your performance. But I think that there is a rich middle ground where we can provide primitives and scaffolding to shape what kind of things we want and need to learn for us to be able to do it well in the world, and that one of our primary goals should be trying to be taking a positive attitude towards architectures and priors, and aiming much more to say, can we build richer architectures that will allow us to learn effectively in much less time and with much less data?
So I guess there is at least one thing where we might perhaps disagree, which is, clearly there's no question that animals and humans learn much faster than whatever machine that we have at our disposal at the moment, whatever methods do we have to train our machines. And the question is whether this is due to prior innate structure or whether this is due to sort of non-task specific learning that's not particularly directed towards a task, but something we could call unsupervised learning, which is not a good term because it's kind of a loaded phrase in machine learning, but the kind of learning that allows babies to distinguish between sounds with more sound categories than their adult counterparts. So, French babies can tell the difference between the and the, but French adults no. American babies can tell the difference between and and American adults not so much, but French adults yes. So, it depends on after you learn how to use sounds for a particular task, which is communication, then you lose the ability to distinguish sounds that don't make a difference in terms of semantics. And so what that tells you is that there's probably some process by which you learn, spontaneously learn categories in a non-task specific fashion. And then, training for a particular task kind of builds on top of this. And so, in a way you could do that, you could think of this as a kind of, it's not a prior structure because it's kind of driven by data and it's still a learning process, but it's not a task-directed learning process. So in fact, the sort of revival of neural nets, if you want, about 15 years ago or so, was built on the idea that was how we were going to train very deep neural nets. We're going to pre-train them unsupervised and then kind of fine-tune them supervised, and that would require fewer samples. We're going to be able to train deep networks with many layers, with not too much problem. It turns out you can actually train very deep networks, just completely supervised, and if you have GPUs and lots of data, it works. So we kind of lost track of the original motivation for deep learning. Coming back to something you said initially, is something we have in common, which is we came to this field because of Chomsky. So, or because we disagree with Chomsky. Back when I was an undergrad in electrical engineering, I stumbled on a book. I think that it was the result of a debate that took place in the late 70s between Chomsky and Jean Piaget, who's the developmental cognitive psychologist. And it was basically a debate between nature and nurture. And on the side of Chomsky, it was people like Jerry Fodor and people like that. And on the side of Piaget was, surprisingly enough, Seymour Papert. The same Seymour Papert who wrote the book that killed the perceptron in the 60s with Marvin Minsky. And here he was, 10 years later, arguing, like singing the praise of the perceptron, arguing for the fact that, here was a machine that was capable of learning, and it was very simple, but yet capable of learning complex concepts. And that was the first time I read about a machine that was able to learn, and I got absolutely fascinated. And like you, I was, I thought all the argument from the Chomsky side had to be wrong, and so that's what got me into that field, really.
So I think there's a lot of we agree with. Where this doesn't, have to be strongly opposed positions, but I still believe that just the current zeitgeist is underappreciating the importance of architecture and how much that is involved in what is producing progress in learning. And so in some sense, there's an older history of something like Chomskyan grammars of these sort of intricately hand-designed things, and intricately hand-designed things were also part of lots of other things, whether it was speech processing or old vision systems. And so in some sense, that's the story there has been we've thrown away all those intricately hand-designed things, and we're making a lot more progress. But I think there's another version of the story, which is to say, those early attempts were trying to hand design things at a way too specific level. And what we want to do is we want to be specifying things at a higher, more architectural level, so our systems have the right kind of primitives to be able to learn well. And I think if you take that viewpoint, you can actually see the history of neural networks in general, but especially the history of neural networks in the last 5 years or so, as actually there are a lot of people that are involved in a search to find architectures that improve learning. And I guess I kind of feel like we should be trying to do more of that. So, I mean, obviously, as is well known, Yann's most famous contribution, convolutional neural networks, is a very specific architecture that's designed to produce translational invariance in a visual scene. That's a really good architectural prior. But, on the other hand, there are lots of other invariances you might want to capture in visual scenes. You might want to capture scale invariances, and you might want to capture rotational invariances. And there are very few people, such as Bruno Olhausen, who have tried to sort of look at models that do that. But that kind of work has been sort of really marginalized in the mainstream vision literature, and it sort of seems like, we should have much more of that. I think I'll sort of mention one specific linguistic example now, and then maybe come back to some more later. So a couple of years ago, Oriol Vinyals and colleagues at Google wrote this paper, Grammar as a Foreign Language. And the idea of that paper was to say, well, we could take a straight off-the-shelf sequence-to-sequence model, have an LSTM encoder, LSTM decoder, and we will be able to learn to parse sentences, that the output of the decoder would put in parentheses, so you've got a kind of S expression that shows you the structure of sentences. So, like, on the one hand, I have to admit it, I was blown away that this was possible. It sort of actually went against my preconceptions of what should be possible, because, and it may be a fancy glorified one, but an LSTM is just a sequence model. You know, it's sort of like a very fancy HMM, and these kind of sequence models just shouldn't be able to learn the kind of nested hierarchical structure you need to put in parse trees, was what I thought. So, you know, when I first saw it, I was blown away, but, you know, then I looked at it a bit more closely and saw that it didn't work at all if you trained it on the kind of training sets that people usually use for parsers. It only worked if you were feeding it 100 times more data, and the way that you generated that data was by using a conventional probabilistic context-free grammar to generate the data, which you then fed it to parse it. And so then I sort of thought, well, wait, this isn't really progress. This is a horribly inefficient learner. It's way worse than the machine learners that we were using in the 1990s for doing language parsing. That's negative progress. But, you know, what happened as a response to that is they said, hey, there's this architectural idea. We could put attention into our sequence-to-sequence encoder-decoder model. And if you do that, well, then actually it can learn to parse sentences in a sequence-to-sequence model with attention and learn over the same kind of amounts of data that traditional methods did. So what drove progress was adding an important new component to the architecture. And I think you're seeing very much in lots and lots of places in what's driving progress in deep learning. It's actually us working out how to design better architectures which give us a better innate priors for learning.
Yeah, I mean, new architectural ideas are, you know, really the majority of papers, at least papers that seem to be capturing the interest of the community at NIPS or iClear or ICML. So yeah, attention, you know, made a huge difference for translation and NLP in general. There's, you know, recursive architectures, you know, convolutional, of course, going back a long time, LSTM, memory networks. I mean, all of those are architectural ideas, and then more recently, capsules, which, you know, are meant to handle more kind of variability than classical convolutional nets. So a lot of those are architectural ideas, and they are what seems to be capturing the interest of the community. The question is, how many of those will survive once we figure out how to, you know, get machines to kind of learn by observation without, you know, being told to solve a particular task? Because I think that's the main limitation. The reason why we need so many samples to train our machines to do anything is because we don't have any way to train them without any task yet. And that's the whole problem of unsupervised learning. So how much structure do we need to put in for some artifact that's capable of unsupervised learning to then come up with concepts like language and recursivity and stuff like that? That's the big question, and, you know, I don't have an answer.
Well, I'll ask you a question further about some of that stuff you were saying. Take advantage of being on the stage. But to say a prelude, yeah, so, I mean, when I started into deep learning, the first area that I worked on a lot was building tree-structured neural networks. And I mean, there was a clear reason for that, which is, you know, I wanted a sort of a general learning architecture, but if I wanted something for language, it seems like the one clear if you have nothing else, if you want an architectural bias for being good at language, that what you want to be able to do is build hierarchical structure, which you can think of as a tree, where smaller units go up into bigger units. And, you know, in some sense, I'll admit that that's only been semi-successful relative to the sequence models. But, you know, I still feel like as science profoundly that is right. Now, you know, for humans and language, well, you know, it's not clear what there is in human brains for language processing. You know, humans do have some special genetic adaptations, et cetera, There may be something language specific, but I think it's equally as likely there's not, and existing structures have been repurposed. And, you know, from that direction, one of the things that could easily have been repurposed is systems initially built for vision. And so from my perspective, Jeff Hinton's suggestions of capsule nets are intriguing. I mean, I don't actually know if the details are right or not, but here's very much an argument from vision that what we want is to have parts-based capsules, which are then fed hierarchically into super capsules for bigger units and repeat that over. And so it's really suggesting building hierarchical part-based structures of the visual scenes, which makes me feel like, whoa, that's exactly what we need. And we can parse with those as well. Yeah. And so, Yann, I mean, do you think that's convincing? Is that the kind of things you think should be being built for the next decade of vision, or do you think that's actually misguided?
Yes and no. I mean, so convnets are of that nature too. They have the idea that somehow you have, you know, a hierarchical structure. And
well, they don't actually provide hierarchical structure.
Of course they do, and that's no, of course they do. That's kind of the whole idea behind it. The fact that you know, you have to reflect the fact that the world is compositional, and the perceptual world is compositional in particular.
What do you mean when you say they're not hierarchical, Chris?
I think the essential difference is whether you have input-specific structure or not. So that the convnet architecture, yeah, it sort of builds up hierarchically, but it's completely uniform, so you're not deciding anything as parts of other things. Whereas even if you had a fixed architecture, I think the capacity that you would need for me to be happy would be to have an ability, which some people have suggested that, you know, brains do in various ways, to sort of carve out a particular active structure for a particular scene. So it's actually recognizing the hierarchical structure of that scene or sentence.
Yeah, but to me that's kind of another type of pooling, right? I mean, you know, you can think of the pooling as kind of a switch that picks interesting parts. And you can have kind of a blind pooling, which, you know, computes a square root of some square, or you can have a slightly less blind pooling, like max pooling, that kind of picks the largest activity, or you can have a pooling that is not really a pooling, that kind of, you know, figures out exactly what part to combine with what part to form objects on the next level. But the question is, can you replace this by just like 3 or 4 layers that are simpler? And I think the jury is still out. You know, we routinely at Facebook use, and everybody in the industry, use convolutional nets that have 50 layers or 100 layers, right? Those ResNet type layers that have kind of skipping connections with identity. And there seems to be an intrinsic value to having many, many layers, because what you get in the end is a system that's able to use many steps of reasoning, very simplified reasoning, to arrive at a decision, as opposed to kind of a fixed number of you know, a relatively small number of layers. So there is perhaps this idea. I mean, certainly compositionality is the motivation for having multi-layer architectures, regardless of what the details are. Now, whether you want to be very explicit, what's explicit about capsules is the manipulation of geometry. So you explicitly say, I want to, you know, encode the position or association parameters of a part or an object with numbers that indicate the you know, the position, angle, and stuff like that. And then, you know, combining two parts of an object to form an object is a linear operation. Whether that's necessary or not, I'm really not sure. It's not clear at all to me. And there are, it's a very interesting idea, and Jeff has been thinking about this for decades. Right?
Yeah. But so something like rotation and variance, is that something you think should be in the architecture, or unnecessary?
So it's not, I mean, it's not clear that we're not born with rotation invariance in our brain. We're not born with weight sharing of the type of a convolutional net in our brain, right? There's no way for neurons to share weights. But there's no need if you're exposed to, if you have some sort of local unsupervised algorithm that just tries to kind of, you know, capture the structure of local structure of images. Any reasonable algorithm of this type, one of which is Bruno Wellshausen's sparse modeling algorithm, will come up with oriented edge detectors, the same kind of features that will emerge from training a convolutional net in supervised mode. So there is, you know, features you can extract that only depend on the input. They have nothing to do with the task you're trying to solve. And if you train an unsupervised system without shared weights, you will have replicated oriented edge detectors in the visual field. So there, the necessity for things like convolutional architectures disappears. So I'm not even convinced that we'll still train convolutional nets 10 years from now. We may not need that prior anymore, depending on how we build our machines. So
Yann, are you saying that the main progress that needs to be made is in a better general purpose learning algorithm rather than a variation on convolutional neural networks, which, for example, captures rotation and other things?
Okay, so there's a statement I'm going to make, which there's a nice slide that goes with it, which I stole from Elio Chaifros, which is that the next AI revolution would be unsupervised. Basically, the obstacle we're facing now in making real progress is how to get machines to learn about the world, learn how the world works by observation with a minimal amount of interactions with it. So that comes back to things you mentioned. Kids learn language with very, very few interactions. They learn the name of objects with very few examples, just a picture book. And that builds on not, in my opinion, not prior structure, but a huge amount of knowledge that's been acquired by observation. But what we could call unsupervised learning, I think we need to find a better name for it. And that's, the big question for me is how do we get machines to do this? And, this is where common sense comes from. So there is, Emmanuel Dupoux, who is a cognitive scientist in Paris we've been working with, and he has this great chart of at what age babies learn very basic concepts, like, the fact that objects are inanimate or animate, right? It's categories that kind of naturally emerge when babies observe the world, and by the age of 2 or 3 months, they've made the difference between those two categories of object, between squishy objects, rigid objects, and objects that are essentially rigid. The fact that when an object is hidden behind another one, it still exists. The concept of object permanence, which Jean Piaget also talked about, that's learned around the age of 3 months or so. And then more sophisticated thing, the fact that when an object is not supported is going to fall, basically gravity, momentum, things like this. Babies learn this by the age of 6 to 8 months. And, babies at that age have extremely limited motor ability. So it's most of what they learn is by observation. There's very little interaction, direct interaction with the world. How does that occur? And in my opinion, that's kind of the big obstacles to, machines that have common sense and things like that. So, back to the point you were making, do we need explicit structures in the brain for language, for example, or for problem solving, or for, certain types of planning and things like this? So one example we could use is orangutans. Orangutans are incredibly smart, almost as smart as we are in many ways. They're not social animals. They don't have language, or at least not the kind of language we're thinking of. The kind of interaction, they only basically, babies interact with their mother, and that's it. So, they don't have the same kind of environment that we do. They are incredibly smart. Like, if by the end of my career we could build machines that were as smart as this, like this would be, unbelievable success.
Yeah, and sorry to interrupt, but we're drawing near the end of the discussion phase.
Great.
So I wanted to actually rewind a little bit and go back to something that Chris said earlier. Chris said, if I didn't mishear, that deep learning has perverted the field of NLP in a way. And he said that this movement towards these more simple learning devices, these fairly simple assumptions about language just being sequences and so on, has produced systems which are actually bad learners. So what would be your response to that? Do you think that this bias towards more simple systems is producing bad learners, or do you have more faith in the ability for these simple systems to learn the structure that we need? Because what I'm hearing from both of you is an agreement that we need a way to learn these primitive structures, but it seems that you perhaps have more faith that these simple systems can learn those primitive structures in an unsupervised way, whereas I'm hearing from Chris that perhaps we need to play a more active role in imposing that structure.
Yeah, I'm not sure they'd be that simple in the end, but I think the prior knowledge will not come from hardwired prior structure, but from unsupervised learning essentially. So I don't see the perversion here, but I see the there is a sense in which I agree, which is we shouldn't. I mean, there's a little bit of a belief somehow that, with either RL or, reinforcement learning or supervised learning, we basically have all the tools we need, and then it's just a matter of kind of finding new architectures to kind of make progress towards AI. And I think that's just not true. We're missing basic principles and things like, like in supervised learning, which is one reason I'm so interested in generative models and adversarial net training and stuff like that.
Oh my, I can't. Yeah, so, I mean, one can't not like unsupervised learning. Clearly, we need to master unsupervised learning, but I think the essential question is going to come down to what do you need in terms of architectures and loss functions and things like that to have successful unsupervised learning. And, I think there is this problem at the moment that sort of very simple architectures have indeed been very successful up to a certain point, and indeed for a number of things there are sort of pressing reasons to make the architectures even simpler because it makes them better in various ways. So, that's where rather than using a sequence model like an LSTM for lots of language processing tasks, if you make it even simpler than a sequence model, like a convolutional neural net for language, well, you can still get great results, and that's computationally much more appealing. So maybe that's what you want to do if you're doing a vast quantity of it. And so there's sort of been this sort of technological push towards simplicity, but I don't actually think that that's right or is going to get us all of the way. And I mean, I think in particular, if, actually there are two things I want to say. So thing one, so there's been this fact that having these sort of everything be continuous vectors, fully differentiable architectures has been such an easy and successful learning paradigm that it makes sense to love it and want to do it. And I can see the appeal of that as well. But I suspect to have successful unsupervised learning, that's not going to cut it, and that we need to do much more in having latent symbolic variables inside our systems where they're making actual choices about structure and state and objects and things like that inside them. And so to me, one of the exciting things that's been happening in the last couple of years is people have been starting to build much better ways in which you can put latent categorical variables into systems and still learn them end to end. And I think, that's exciting. We're still in the very early days of modern deep learning, and we want to see much more of that, and I encourage people to be trying to do more than that. And that relates to a comment. Yeah, so we want unsupervised learning. Personally, I kind of think that we're never going to get the kind of intelligent systems that use knowledge, reasoning, memory, planning, and all of those kind of things if our objective function is simply at the surface level, that if we're predicting pixels in a visual scene or we're using a language modeling objective and that's all we've got. I think that just isn't going to be sufficient, that I think we need to have things in our system where essentially it is being forced to abstract structure, and so that prediction can be done in terms of abstracted structure, which leads into the same kind of interest in symbolic representations. And Evie wants me to stop.
Yann, I think this is your last bit before we go to questions, so let's try to wrap it up.
I think we should go to questions.
You want to go straight to questions? Okay, fine. There's 2 microphones on each side of the auditorium, so please go ahead and line up behind the microphones if you want to ask a question. When you ask your question, can you please give your name and your affiliation? And also, we are only going to have 1 question per person. Okay, let's start on the right over here.
Hi, my name is Ray. I'm a first-year PhD student currently rotating a microcognitive lab. I have a question regarding this notion of implicit regularization. So what we've discussed a lot about architecture as a kind of explicit constraint on your model, but what hasn't occurred in this discussion yet is this idea of like whether or not there's any implicit regularization when you use SGD combined with perhaps the layer-by-layer parameterization that we see in a neural network. And recently, we've been seeing a lot of people considering this. Why is it that neural networks even generalize to begin with? And so I think some people are strongly believing that some implicit regularization is happening. So all these discussions about architectural constraints could be like the tip of the iceberg. And even without these constraints, simply the fact that we're using neural networks of SGD could itself be this massive amount of regularization that we're not discussing. Should we be considering that sort of regularization with a bit more care?
I think there is more to the implicit regularization of neural net than just the effect of SGD. I mean, certainly SGD has an effect because it drives the system towards robust solutions. But they do work without SGD. It's just learning is slow. So it's been a bit of a mystery, I guess, and perhaps one of the causes of disbelief from people who are kind of more grounded in theory about why neural networks work. That neural nets to some extent break all the rules of statistics, right? They have many more parameters than you have training samples most of the time. And the bigger you make them, the better they work. I mean, how does that happen? It's just the first page.
Is that always true? Is it always true that the bigger you make them? Yeah. I thought there was a paper that showed that sometimes more layers makes it worse.
Yeah, no. I mean, they basically work better if you make them bigger. I mean, it's not an absolute rule, obviously, and there are limitations to that, but. And sometimes you need a little bit of explicit regularization, like dropout or things like this. But it improves a bit. It works without it as well. So it's a bit of a theoretical mystery, which I think is very interesting from the mathematical point of view. That quite a few people are working on. I'm actually co-organizing a workshop next week at IPAM at UCLA on kind of new methods in deep learning, and some of the questions are revolve around this. A bit of a mystery.
Thank you.
Next question from this side.
Hi, my name is Alex. I'm a senior at Stanford. Chris, you mentioned earlier the phrase good learner when you were talking about children and comparing them to neural networks. There's lots of different ways to express what a good learner is. You could talk about sample complexity, 0, 1, or few-shot learning. You could talk about performance. You could talk about generalization in different scenarios. And it seems to me like that concept of a good learner would influence, whether you think that prior structure, what kind of prior structure is needed for a certain end. So could you elaborate a bit more what you mean when you talk about good learners and how that influences this discussion about priors?
Sure. So I think what I was primarily invoking was sample complexity, that you want to have things that are few-shot learners, and that's clearly very much evoked with how human beings learn. But I think I sort of think that there's another sense, which I don't actually know how to formalize in machine learning terms, but I'll say it anyway, which is in some sense a deep learner in a different sense of something that actually makes abstractions, and so that can describe things in terms of abstractions. And what I'm sort of meaning by there is, there's this way in which if you can have infinitely large models, those LSTMs with 2048 size vectors, and you're being given infinitely much data, you don't actually have to build the right abstractions inside your model. You can just sort of effectively be doing glorified nearest neighbor learning. And I think that shouldn't be our goal. I think we should be looking for learners that actually really are learning good abstractions for the domains that they're working in.
Glorified nearest neighbor is the phrase I used to qualify supervector machines when I was trying to convince people that deep learning was a good idea.
Yeah, and to generalize that point a bit, do you think that it's possible that the way we formulate our tasks in the deep learning era is perhaps masking these problems that Chris is alluding to, that we're not building the kind of representations we need of the primitives, but that effect is being masked by the way that we formulate the tasks as, glorified nearest neighbors?
Well, one of the main conferences on the topic is called the International Conference on Learning Representations, which means that it's completely front and center the main issue that deep learning has been trying to address, how you build representations.
I take some credit for that name. I argued for it.
Thank you. Well, you were invited speaker at the first
No, I was
edition.
the program chair.
You were so program chair. Were you invited speaker at the second one then? At some point. I mean, it's all about learning representations, hierarchical representation. So then the question is, perhaps what structure you need, what type or what paradigm of learning do you need? In the end, you have to ground this in whatever variables are observed. So you said, it has to go beyond just pixels for images and characters or words for text. But what else do you have? And so that's really the big mystery. It's how you build abstract representation from observed data, in my opinion, with data that is not task-oriented, so unsupervised, whatever that means. That's really a big question.
Okay, next question.
Hi, my name is Arun. So I'm a PhD at the Stanford NLP group. So hi, both of you. My question is one that I've heard Andy Bartow from the RL fame raise, and I really don't know if there's an answer to this, which is where does reward come from? And I will phrase this in another way to ask whether, Chris, you believe that as babies or as people, we have some innate sources of reward that tells us, like when we touch something, it hurts and we get some signal. And I don't know to what extent we have other signals as babies. And is this a sort of innate prior that you consider? And but in general, where do we get supervision from? Where do we get rewards from if we're doing unsupervised learning or
I think in principle it's easy to see how you can get supervision, or reward, I should say, in unsupervised learning. Like human beings, I think, innately want to understand how the world works. So if things go the way you think they will, you're happy, and if things don't go the way you think they will, you're unhappy. And I think that is a self-rewarding system.
Yeah, but that's an intrinsic reward, if you want. So it's not a reward that comes to you from the environment, from the world. It's a reward that you compute, your brain computes, makes you happy because you predicted something that actually occurred. Or you modified your model of the world in such a way that now you would be able to predict what actually occurred. So, this is something that I was mentioning Emmanuel Dupuy before. So the way you test whether babies have understood the concept or not is that you show them something and that breaks the physics. So for example, an object that floats in the air, and you see if they're surprised or not. If they are less than 6 months old, they say, sure, that's how the world works, fine, no problem. After 8 months, they go like this, right? Because their model of the world is broken. Therefore, they have to pay attention to modify it, because if your model of the world is wrong, you can get eaten or whatever. So.
So you just both outlined how humans have this internal model of the world, and having a good model of the world is its own innate reward. But how do you see that applying to artificial intelligence?
So the thing is, pure. I mean, I've been making this point, many times in the past, with the cake analogy, right, where reinforcement learning is the cherry on the cake. If intelligence is a whole cake. And the reason I make that point is because if you rely purely on external reward to learn a task, the sample complexity of this is so horrible that you're not going to learn anything. You're going to learn to play Go by playing, 5 million Go games, but and that works really well, and that's amazing. But in the real world, you can't run a car off a cliff 50,000 times before you figure out how not to run off a cliff. So this kind of learning obviously is insufficient in the real world. And so a lot of people in robotics are actually trying to figure out how you learn things with a minimal interaction with the world, because every interaction with the world you're doing costs a lot. It costs time, and it might kill you.
So it seems like we're hearing an agreement here that reward should be innate, and that this is a crucial piece of making a more general.
It should be intrinsic, and the feedback you should get from the world should be much, much, much richer than just one reward once in a while. It should be predict everything from everything else. So predict the future from the past, predict the past from the present, predicts the back of the object you're not seeing, predict everything from everything else. That's it's a principle that I didn't invent. Jeff Hinton has been talking about things like this for 35 years, if not more.
Okay, next question on this side.
Hi, I'm Andre, a CS master student at the Stanford Vision Lab. A common observation has been that feature engineering has basically been replaced with network engineering, figuring out the right priors to put in. And we might be hitting diminishing returns already. And an emerging field has been evolving neural net structures, so evolving the basic CNN block or evolving a sequence component. So do you think this new area of work of evolving neural net structures can be promising for doing away with priors?
It's a much better use of GPUs than beacon mining. Yeah, I mean, certainly that's kind of back to the point I was making earlier, that with increased computation, increased data, there is a lot of things you can learn that you wouldn't think about learning before. And so that, I think is another example of this kind where you need more data when you do this because every model you train, you use your data, and if you use it too much, then you need a validation set for each of those, and so you need large data sets to be able to do this, and of course you need a lot of computation. So I think it's the next step in the curve of diminishing prior structure enabled by larger data sets and more computation. Yeah, it's a good thing.
Do you have anything you want to add, Chris, or should we have another question?
I'll just very quickly say, I do think that work's interesting. I think there's sort of a lot more to think about and do to come up with interesting architectures. I mean, I think it's the initial work, but the initial work is sort of, we have 5 Lego blocks, and I'm going to stick them together in the ways that they fit. And I think more will need to be done from that to come up with interesting architectures as evolutionary.
Okay, next question from this side.
Yeah, so you mentioned this intuition that the more data we have, the less structure our networks will have. I guess to me, from a vision perspective, it kind of seems like it's the opposite. Like, we, on top of convolutional neural networks, which is structure, we've added like channel-wise followed by depth-wise convolutions, which is culling more connections, and we've added attention, which is another example of like adding more structure, and these things seem to help a lot, and they help even when we have more data. Like if you multiply the amount of data you have by 100 or 10, it's still better to have these extra structures. Do you think that it's just I'm not interpreting that correctly, or?
Well, I mean, certainly you need to have the right sort of basic primitives, and certain primitives are going to do a better job, regardless of how much data you have. But some of them are due to so for example, the ResNet idea, right, that you have skipping connection. It's kind of a way of making the optimization robust, so that if one layer dies or does something completely wrong, it kind of gets out of the system and it's ignored, and the data bypasses it. Whereas, if you have a classical kind of, neural net without pass-through, if one layer does something wrong, then the whole thing, basically fails. So, so that's kind of a way to fix, optimization issues, basically, that might be fixed some other ways. Now, let me
sorry, can I just interject for a moment? While we're talking about, for example, residual connections, would you view, and this is a question for both of you, these kinds of fixes to optimization problems, would you view that as a kind of deliberate, principled design decision that is based on some deliberate innate prior, or is it more of a hack to fix a problem that's going wrong?
Neither. I think it's like a meta level. I mean, it's sort of more kind of a substrate that you need to have for things to work. But to answer your question more precisely, if we were to train a neural net without the convolutional constraints, okay, still local connections, but no equality constraints, but we were training it by systematically shifting all the samples that we have, we would get the same result. It would take a long time, a lot more effort, but it would basically work the same in the end. So even convolutions, I think, are not absolutely necessary. It's just that it's a good way to cut down training time, number of samples required, robustness, whatever.
I think I'd differ a bit and actually say it's a deliberate good design decision, that essentially it's sort of replicating in the vertical direction the success of the LSTM idea in the horizontal direction. And I think that's a good design decision. That's saying we want to have a model that can support long-term memories in a sort of a natural low effort way, and that is a good thing that correctly models the kind of priors that we want to build into our system. So I actually think that is a good thing. I mean, I think I share what you're saying as to saying that actually people are building more and more complex architectures to try and get neural nets that do more and more. And I just think actually one should be hopeful about that because things are trending in the right way. And I think it's sort of not too surprising that those more complex architectures help even when you have a lot more data, because the fact of the matter is that sort of most of the inefficiencies that you try to fight against from bad learning architectures are at least polynomial, if not exponential. So it's not surprising that the better architecture is still useful when you have 10 times as much data.
Okay, we're going to have a few more questions. I know it's 4 o'clock, so if you need to go, it's 5 o'clock, so if you need to go, please go ahead. But we did start about 5 minutes late, so we're going to keep going for another 5 minutes. Okay, let's have another question from over here.
Thank you. Hi, I'm Rick Caillé. I'm with Qualcomm Research. Yann, thanks a lot for your talk. I think you both outlined the problem, right? This is the problem with today's deep learning. So what do you think about potential solutions? And I don't want to jump to the solution, but for instance, we're seeing recent mashups of knowledge graphs with convolutional nets. And I think, Yann, you talked about the case of the baby that didn't see the object drop. They have a physical model somehow that they built in their head. So what about online physical models or models of objects? Sort of all boils down to some sort of knowledge base or knowledge graph, mixing with.
Yeah, I mean, there's a question of knowledge representation. How do you represent your intuitive notion of physics? How is it that when we face a new situation that we've never faced before, we can immediately build a mental model of that situation that will allow us to plan and arrive at a particular result that we're looking for. So we seem to have some sort of, perhaps somewhere in our prefrontal cortex, some sort of generic world simulator that we can configure to any particular situation. And that, is perhaps an example of, of where we need some sort of structure. But the first part of your question, I guess, relates to what I was talking about earlier of kind of merging machine learning with reasoning. So replacing symbols by vectors, essentially, or tensors. And replacing logic by algebra. That also relates to some work that Chris has been doing on those recursive networks. And there's a beautiful paper by Léon Bottou from quite a few years ago, I think 2011 or so, but he had been talking about this for 3 years before that, on the idea that you should have operations that take 2 objects from a representational space, whatever it is, 2 or more objects, and combine them into a single one, but put the result in the same space. So this is very different from like multilayer architectures, where the representation at one level produces representation at the next level, but it's not the same space. So if you map back to the same space, you can have chains of reasoning. You can have, with a non-definite number of operations, and this is really the basis for things like recursive networks and stuff like that. And I mean, I'm a big fan of this kind of stuff. I think it's great. So. I'm not against structure from that point of view, certainly. Yeah.
So I basically agree. I think we're going to see a lot more richer architectures. I mean, memory is clearly one of the central things that we need to do more of, and there are a bunch of different ideas for doing that. Having more in this multi-step reasoning that Yann was just talking about is very necessary.
Okay, unfortunately, we've only got time for one more question, and it will have to be quite a fast one.
Okay. Hi, I'm Michael Wainberg. I'm a CS PhD student here. It seems like the core reason that humans are good at language and computers aren't is that we've had a billion years of reinforcement learning on a really general objective function, which is like survival, reproduction. Is that an argument in favor of more structure or less? And are there lessons we can take from evolution as an optimization process as we move towards general AI?
So language appeared in the last 300,000 years, maybe. maybe a little more, but not much. So in terms of evolutionary time, it's actually extremely recent. We sort of branched off from big apes about 5 million years ago or so, and humanity has, modern humans appeared about 300,000 years ago or so. It's quite certain that Neanderthals had language, and they popped up a few 100,000 years before that. But language is sort of a, sorry about this, you may disagree, but it's sort of a bit of an epiphenomenon. I mean, it's not that complicated, because it popped up in. I mean, again, let's take the example of orangutans. They are almost as smart as we are, in terms of like representation of the world, predictivity, interaction, planning, building stuff. I mean, they do amazing stuff, and they don't have language. So, there is a lot to intelligence that has absolutely nothing to do with language, and that's where we should attack things first. I mean, obviously, we're very interested in language at Facebook, for various reasons. That's not what I want to say, but I mean, there's a lot of super interesting work going on there, all the way from like super shallow learning to very deep one. But and so there's practical applications for this in translation and all that kinds of stuff. But in the general scheme of things, I would say language is is number 300 in the list of 500 problems that we need to face or something.
Well, Yann waited till right at the end to bring that up. What I would suggest is that even if orangutans, whales, or octopuses have more intelligence.
Shouldn't linguists know what the plural of octopus is?
More intelligence than you'd think. What's actually interesting is that language has been completely transformative because it has allowed the emergence of a social intelligence, that rather than just having an individual who's figured out and knows some things, you then have an entire society that provides a kind of a hive mind in which people can have a shared memory, shared knowledge, shared ideas, and build on top of that. And it seems like language has been way more successful than things like having poisonous claws or being able to run fast in producing a huge amount of advance for humans as a species. So I reckon language is not so bad.
So you wouldn't rank it number 300 out of 500? You'd rank it somewhere higher than 300? Okay, unfortunately we've got to bring the event to an end there. So thank you so much to everyone for showing up. And thank you so much to Chris and Yann for taking part in this. Thanks, everyone.